Okay. Um, Organic chemistry is made up of um, carbon-based compounds, and the simplest ones are called alkanes and alkenes. And then they keep adding other things to it. They're called functional groups. And the functional groups determine the behavior of that molecule, whether it's polar or non-polar, whether it's reactive, non-reactive. So we're going to be going through 4 units in this class. Unit 1 is the alkanes, alkenes, and alcohols and ethers. Now, there's physical properties associated with each one. There are reactions associated with each one, and that's kind of the basis. So today I'm going to talk about alkanes. The other thing I want to talk about is how do you write a structure? Now, you're going to be writing structures from here to the end of the semester, every day, structures. Organic chemists and biochemists hate writing hydrogen H's on everything. They also hate writing C's on everything. So they've developed a shorthand way of writing structures. It's called a line drawing. I want to demonstrate that real quickly for you once we get into this. Okay, so alkanes are made up of carbons and hydrogens only, single bonds only. Now, 305 was inorganic chemistry. 306 is organic chemistry. That means we're looking at 99.999% of the molecules we're dealing with are carbon-based. There are a lot more organic molecules than inorganic molecules by a huge margin. I don't think this is accurate. I think it's more than 6 million. There's a bunch. And they're being more and more made by the hour. Just a whole bunch. Inorganic stuff is the stuff that usually doesn't contain carbon. It can include carbon, mainly it doesn't though. Organic compounds differ dramatically from inorganic compounds. They're covalently bound, mostly, not 100%. They're often flammable. Who knows the difference between flammable and inflammable? Sorry? No. Once you pass a gasoline truck, it'll say inflammable. Okay, inflammable is a wrong way to describe what's in the gasoline truck. They should say flammable. Inflammable means it's not flammable. In other words, it won't burn. For example, water, inflammable. Gasoline, flammable. So that's the big difference, okay? And that's frequently misused. Usually they don't conduct electricity. Acids, organic acids, however, conduct electricity quite nicely. There's some other ones as well, but mostly they don't conduct electricity. That means they're not ionic. Rate of chemical reaction, slow. Usually, there's a lot of exceptions. Think about when you start your car in the morning. That's a pretty fast reaction going on in your engine. Really fast. So it's usually. Okay, now, carbons have 4 bonds, either 4 single bonds, a double and 2 singles, 2 doubles, a triple and a single. Total of 4. No exceptions. Okay. Now, a double bond counts as 2 bonds. A triple bond counts as 3 bonds. Okay, so if we look at Let's look at this here. 3 carbons and a whole bunch of hydrogens. Okay, the way to do a line drawing looks like this. That molecule. A lot simpler. Now, students in the beginning sort of don't like the line drawings, and after a while they go, every textbook I've used, except the one that provided these PowerPoints, uses line drawings. So the deal is a carbon is located at the beginning, at the end, and in every kink. 3 kinks, each one of those is a carbon. So in this case, we have 3 carbons. So we have one in the beginning, 1 kink in the middle, and 1 at the end. So when we're dealing with carbons and hydrogens, we only want to use line drawings. Otherwise, you're going to be drawing this is not tracking. I need to do one correction. See where the dot is and the tip of my pen? They should be together rather than like this. We'll just have to get around that. Okay. Okay, my point here is that's a lot simpler than that. Now, we're going to be covering in Unit 2 carbohydrates. Carbohydrates this is glucose I'm drawing. This is alpha D glucose. Now you're going to know this molecule intimately in Unit 2. But my point is, there's a lot of carbons there. There's 6 carbons. And there's a whole bunch of hydrogens as opposed to the line drawing here. So line drawings really save you a lot of time. Okay. There's another term that you might have gone over in 305. That's something called isomers. An isomer has the same formula, but different structures. For example, that right there, C2H6O, has 2 isomers. Ethyl alcohol, which is drinking alcohol, and dimethyl ether. 2 carbons, 6 hydrogens, 1 oxygen. So those are isomers of one another. Now we're going to cover both of these in this Unit 1. My point is isomers, same formula, different structure. There's also something called geometric isomers. Geometric isomers are like your hand. left, right. One palm, one palm. 5 fingers, 5 fingers. One thumb, one thumb. Yet they are totally different. So this would be a geometric isomer. Now our body biochemically is designed to differentiate between this and that. And the active site of an enzyme is extremely specific. Who's heard of thalidomide? Anyone? Okay. Thalidomide was a disaster. It's an anti-nausea medication given to women in their first trimester. A disaster because it came two forms. One form was anti-nausea, the other was a teratogen. Who knows what a teratogen is? Anyone? Causes birth defects. These children that were born had no arms and legs. It was more of that in Europe than the United States, but the United States had a fair number as well. And it had to do with when they manufactured the thalidomide, it produced both the D and the L form, not just one or the other. Huge disaster. Huge. Another interesting thing on this whole isomer thing. Who has a problem with MSG? Anyone? Okay, MSG stands for monosodium glutamate. It's based on the amino acid glutamic acid. There are two forms of it, D and L. When you buy MSG, you get both. Your body makes glutamic acid. It's not an essential amino acid. Yeah, some people are allergic and have reactions to the one our body doesn't make. Okay, it's the D form our body doesn't make, not the L form. So this concept of isomers is very prevalent biochemically and organic chemistry as well. Very prevalent. Okay, okay, so this concept of isomers, that makes sense? Now, what differentiates one organic molecule from another, besides the number of carbons, besides the number of bonds, etc., are something called functional groups. Functional groups are things like an OH group there to make it an alcohol, a carbon, oxygen, carbon to make it an ether, a NH2 to make it an amine. All these are called functional groups. They make the molecule have certain characteristics, certain reactivities. And unit 1 functional groups are OH, alcohols, and COC, ethers. Those are the two functional groups we're going to focus on. Okay, I already talked about this. Okay, I'm sure you also heard of the term hydrocarbons. Hydro means H, carbons mean C. So if the compound only has C and H's in it, then it's a hydrocarbon. Hydrocarbons are a real problem with the world, especially countries that don't like alternative energy sources. In other words, coal burning, natural gas burning, because they create hydrocarbons. That's called a greenhouse gas. Of course, so do cows. But, you know. So anyway, it's a real problem. Hydrocarbons burn quite well. Now, these are the different groups of hydrocarbons. We are not going to talk about this one because our body contains no triple bonds. And in this class, we're only talking about biochemical molecules in our mammalian organisms. Okay, no triple bonds. Now, you may take a drug that's got a triple bond in it, but naturally, we don't make them. Okay. Okay, so this is alkanes we're talking about today. If the molecule has only single carbon-carbon or carbon-H bonds, it's called a saturated. We're going to get into this in lots of detail when we talk about fatty acids. There's saturated and unsaturated fatty acids. Okay, if it has a double or triple bond or aromatic, is considered unsaturated. Okay, so the concept of saturation has to do with whether the hydrogens are located in the double bond or the triple bond. And we'll get into that again in a minute here. Okay. So another thing when we talk about naming, we're going to get into naming here in a minute. They this slide goes into detail about the formula for these, whether it's cyclic, whether it's linear, etc. I'm not focused on that at all. Just know there's a general formula for alkanes and whether they're cyclic or non-cyclic. Now, this is where it gets interesting. We can have a straight chain carbon backbone. And when I say backbone, we're going to get into what a backbone is and what a branch is in a minute. The backbone has the most carbons that includes the functional group. Most carbons includes the functional group. Now with alkanes, the functional group is a hydrogen, which is sort of not a functional group, but anyway, it's so what I do is I take and the marker, I take and put yellow as the backbone. Now, anything that's not on the yellow backbone is called a branch. Now, sometimes we have primary backbones and secondary backbones. That's Unit 2 stuff. But for this Unit 1, there's only one backbone. Okay, so in the case of this over here, that's the longest chain, one in the middle. Now, you have to ask yourself, are there carbons not on the backbone, not on the yellow? Yes, that means this one here is branched. In fact, there's two branches. Two one-carbon branches, two methyl branches. Okay, on the one on the left, is there a carbon that's not on the yellow backbone? No. So that's non-branched. So we have no branches on the left, two branches on the right. I'm going to get into this. What does that mean? That stands for normal. Yeah. Okay, normal. Now, this has got four carbons, right? Four carbons. Now, let's look at the backbone first. That's the backbone. If the backbone has got four carbons in one branch, it's called isobutane. Iso now I'm old, and I don't memorize very well. So I have these little ways to remember things. I think of ISO like a snake's tongue. What does a snake's tongue look like? Right? Now, if we drew this with a line drawing, it's going to look like this. Okay, so we have beginning carbon, end carbon, kink. So that's the backbone, one branch. Okay. Now we can have branches that are isobutyl as well. All that's going to come up on a chart here. Now, I don't want to do that. Now, the thing about carbon-carbon single bonds is they can freely rotate. Double bonds cannot, they're rigid. So that means if we have four carbon molecules, we can have a bunch of different variations on that. Some are better than others. When I say better, I mean more stable. The stability rules the game in the universe. If something's going to become more unstable by reacting, it won't happen. If it becomes more stable, it'll happen. And when you study that in 305, I don't know if you got into delta G's and all that stuff. Okay, yeah, so the lower the delta G, the Gibbs free energy, the more stable it is. So let's look at these two here. We've got one on the left, has got one configuration based on these guys just moving around. The other one is kind of like a boat. Which do you think is more stable, one on the left or the right? Okay, we have the right. Who votes for right? Raise your hand. Okay, guess what? You're all wrong. One on the left is more stable. This is why. Okay, when a group can be by itself more stable. Over here, we have this thing is swung around so that we have this interaction. Not stable. It's stable, but not as stable as the one on the left. So this is called steric hindrance. And that'll determine shape. It also determines how easily a reaction will go. If something is sterically hindered, where the other molecule can't get at it, the reaction rate will be very low. If it's wide open, reaction rate will be fastest. So the steric hindrance comes into play a lot. Okay, because carbon-carbon single bonds can freely rotate, we have 5-carbon alkane here. We can freely rotate this thing a lot of different ways, and it's the same molecule. Okay, so let's look at the look at the top two. How many carbons are in the yellow backbone? 5, right? The one on the right, 5. Now let's look at the bottom two. Okay. How many carbons are in the backbone? So this is not the same molecule as the one above. One above is an isomer of this one. So this one has a branch. Now, there are two ways to draw the backbone. In this case, that's another alternate backbone, also four carbons long. So both are equivalent. So it doesn't matter which one you choose, because I can make this by twisting it to be equal to both. Okay, let's look at this one over here on the right. That's four carbons long. If we choose the horizontal one, it's only three long. Four is bigger than three. Tough math, huh? Okay, so the yellow one is not valid in this case as a backbone, only the orange one. Four carbons long. On carbon number 1, 2, we've got a branch. Carbon number 1, 2, we have a branch. So those two are equivalent as long as we use the orange one on the right's backbone, not the yellow one. Now, when we start naming this stuff, you have to determine the first step is what's the backbone? Step number 2, are there any branches? Step number 3, this is every single one now. Step number 3, what's the functional group? When you start naming this stuff, yeah.
Is the thing that determines a monoalkane versus a branched alkane determined by whichever has a longer backbone? Okay, sorry.
Yeah. When you name stuff, there are three parts. The middle part is how long the backbone is. And that's based on, I'll show you a table in a minute, how to name it. Okay, so all these 5 carbons, all these are 12 hydrogens, but they aren't the same. Like these two, same thing. No branches, 5 carbon backbones. They just twisted. And you have to keep this in mind when you're figuring out how to name this stuff. Same with this one, 4 carbon backbone, left and right. Okay, so this is okay, we start naming this stuff. It's all in 3 parts, like I mentioned a few minutes ago. One part is optional. Okay, the middle one is the backbone length. The third one on the right is the functional group name. The one at the beginning is branches. You can have 1, 2, 3, lots of branches, or just one, or none at all. If there are none, you just leave it off. Okay, when we start naming them, if there's a branch, it's different than the structure. Okay, so if a branch has got one carbon long, it's called a methyl. 2 carbons long, ethyl, 3 propyl. Okay, I'll show you a table in a minute here. Okay, so that's okay. When we start getting bigger branches, more complex branches, there are many versions of that. For example, if we have a 3 carbon branch, it's in 2 forms. Isopropyl, remember the snake, or N-propyl. N means straight, normal. When we have 4 carbon branches, there are more versions available. Now, I'm going to hold you to these guys, but not these guys. I want you to understand it. I don't want you don't need to memorize them. Yeah.
Like the slides are going to be available.
Or what?
Are the slides going to be available on campus?
Yes, in fact, her question was, are the slides available? To study this class, the most efficient way to study is to look at my lecture schedule and figure out what my lecture is. That it's on alkanes. 2 days ago, you could have downloaded the slides. I'm going to show you what's available on Canvas, and then gone to last semester's video on alkanes. Print off your slide and then take notes on the slide. So when you come here today, it'll be review. And parts you didn't understand, you can ask questions about. That's the most efficient way. Takes more time, but it's highly successful. And I'm talking about decades of teaching this class. For decades, I've been doing videos of my lectures. Okay, so let's stop a second. And I'll show you where the slides are located. Thank you for asking a question, by the way. Okay, here I am in my tie-dye lab coat. We're going to go to Files. Unit 1. Slides. And there they are. Under worksheets, here I broke up Unit 1 dry lab into separate worksheets, if you'd like to do it that way. So here's Unit 1 dry labs. They're also under lab related. By the way, while I'm here, this is the waiver file. Download that, print it, scan it, upload it into assignments. And here's the lab safety contract. Same thing. Now you don't have to download this if you want to. I'm going to give you an inventory for your drawer when you get into lab. And on the back of the inventory is the safety contract. So you can either do it digitally or you can sign it and then scan it and upload it. Okay, try to get those in this week. Remember, easy peasy, 10 points apiece. Maximize the easy points. And by the way, unless you sign both of those, you cannot participate in labs in this class. This is a lab class. You have to pass lab to pass the class. So not only is it easy points, it's required, particularly the waiver. They're real picky about that. All the schools in the state of California have this waiver. Doesn't matter what school you're at. Okay, so are there any questions about where to find the slides, the lab safety contract, and the waiver? Okay. Let's go back to okay, a branch can also be a non-carbon. Now, the ones that so these two, chloro and bromo, are more frequently used. Fluorine is not very nice in your body. And for all you dental-related students, every toothpaste has got what in it? Sodium fluoride, yeah. I have horribly stained teeth. I was born in Texas, Lubbock, Texas, in the panhandle of Texas, and they heavily fluoridated the water in the 50s. Guess what it does to teeth? Stains the dickens out of them. And you can buff it out and all this stuff, and they're still ugly. I'm glad I have long lips. It covers my teeth. Okay, nitro and amino. I'm going to get into those in follow-on units. Okay, so anyway, bottom line is these are all branches. Okay, so here are the three parts of naming. Now, there are two ways to name. IUPAC, International Union of Applied and International Union of Pure and Applied Chemists. Okay, three parts. We have a prefix, which means branches, the backbone in the middle, and the ending is the functional class. Each functional class has a unique ending. Like alkanes ending, they all end in A-N-E. Alkenes end in E-N, E-N-E, alkenes. Alcohols end in O-L. So they have a unique ending. This is backbone. And this one is optional. Okay, no branches, leave it off. Okay, so when we're naming the backbone, we are going to be using these here. Now you need to know these up to 10, but this goes on up huge numbers. But these are the main ones, particularly these guys. Okay, so let's look at this molecule here. Okay, I'm going to draw this line drawing. Okay, it's got bond. First of all, identify the backbone. Backbone is going to be here. And carbon number 2 can go up also. And now, notice I've numbered the carbons on the backbone. It's real important. You have to number the carbons on the backbone. Two ways to number, starting from the left, starting from the right. Okay, I'm going to show you which one you're going to be preferred. Okay, number 2 is, are there any carbons not on the backbone? Yeah, right here. Okay, so we're going to have a branch. 5 carbons long, it's going to be a penta. And we have 1 branch. Okay, so let's. One, two, three, four, 5. Okay. Beginning is a carbon, ending is a carbon, and we have 3 kinks, also carbons, 5 total. Okay, now, what you start to do is you're going to start naming the start the backbone now. That show it very well. Yeah, actually shows up better up there than that. Okay, so let's name now. Okay, so if we start from left to right, 1, 2, 3, 4, 5, starting on the left, we can number from the right to the left as well. And we are going to use a different color for that. Okay. Now, which one's right? Look at the branch. Okay, the branch is either on carbon number 4 or carbon number 2. I want to choose the one with a lower number for the branch. So the one with carbon number 2 is the correct one. Now, the reason why I focus on naming is for you to pay attention to structure. On the test, if you name this, instead of 2-methylpentane, you named it 4-methylpentane, I would take off 1 point out of 6. That's why I don't do multiple choice. Multiple choice are right or wrong. 0 or full credit, yeah.
What does the 2 stand for again?
What carbon is a branch on? Okay, look at the backbone. Okay, we've got, this is supposed to be blue. It looked like it's black. Yeah, dark blue, anyway. Naming on the right, we go 1, 2 is a branch. If we start on the left, it's on carbon number 4. Okay, and we always want to use the lower numbered ones. So okay, 4-methylpentane, okay? 3 parts, remember now, okay? That's how long the backbone is. Functional group. A and E is an alkane. And because we have a branch on carbon number 4 or carbon number 2, it's 1 carbon long, so it's a methyl branch. And that one is more correct because the number is lower.
Is A and used for alkanes?
Hmm?
Is A and used for alkanes?
Yes.
Okay.
Think of the word alkane at the end. Alkane, E-N-E. And Wednesday, we're going to get into alkenes, E-N-E. All right, So we can have multiple branches. Okay, so let's do this as a line draw. Okay, we've got 7 on the backbone. So we're gonna go 1, 2, 3, 4, 5, 6, 7. Now, the way I do it is as my pen is on the paper, I go 1. And then go however many I need to do. Okay? All right, so we've got a branch. Let's say the way the numbering is there is more applicable because the numbers are all basically on the left. So if we start on the left, the numbers will be lower. So this is going to be carbon number 4. We've got three carbon branch. Carbons 2 and 3, we've got a 1 carbon branch. Now, if we started numbering on the right, our first branch would be 1, 2, 3, 4. If we number on the left, our first branch is on carbon number 2. That's why the numbering on the left is better than the numbering on the right. Okay, so we have to identify what the branches are. These are 1 carbon, 3 carbon. And they differ. Okay, the 2 methyls, how many mono, di, tri, penta? How many are 2? Di. So we have a dimethyl. We have to identify what carbons the branches take off from. Okay, in this case, it's going to be 2, 3. Okay, we've got a 3 carbon one, and this is going to be the snake branch, isopropyl. That's on carbon number 4. We've got a 7 carbon backbone. And it's an alkane. Okay, so remember 3 parts. Do we have branches? Yes, those come first. Now there's a deal with if you have more than one branch type. In this case, we have a methyl and an isopropyl. Which goes first? Alphabetically. I before M. So the isopropyl comes first. Then comes the shorter ones. Branch length is hepta, which is 7. And the functional group is an alkane, so it's ANE. Three parts.
That everything. Yeah.
Yeah, but my writing is horrible because my stylus isn't tracking. So I'm off, so I'm writing like this. It's kind of. Okay. Does that make sense? You just have to practice these a lot. Hence my dry labs. A lot of practice doing this. Do you have a question?
Is every 3 branch, 3 carbon branch always goes on isopropyl?
No. Either propyl or isopropyl. Depends where it attaches. If it attaches on the end, it's propyl. If it attaches in the middle, it's isopropyl.
Thank you.
All right. The other thing is, okay, we've not talked about cyclic compounds at all, particularly biochemically. Most biochemicals are cyclic in nature. The reason why is cyclic things tend to be more stable than long, skinny things. More like when the wagon trains were heading west. When they wanted to defend themselves, they didn't stay in a long string. They circled up because it's more stable. Same thing with molecules. The more stable molecules are the cyclic ones. Okay, when we name it, though, we have to refer to that as a cyclo backbone. Depending on the length, okay. The 6-membered ring is the most stable. The 3-membered ring is very, very unstable, meaning that it won't sit around long in the jar. It'll want to react. Where the cyclohexane, 6-membered ring, very stable. They'll sit there forever. Okay. Let's look at this guy here. So we've got a 5-membered ring. We have 2 branches. Now the cyclic part automatically identifies the backbone. Automatically. Excuse me. Okay, so we've got penta, 5-membered cyclic, so it's going to be a a 5-carbon cyclic backbone. And we have an ethyl and a methyl branch. Okay, again, 3 parts. Okay, let's name the branches first. Which should we put first? Ethyl or methyl? Ethyl. E comes before M. And the ethyl is on carbon number 1. Now, when you have cyclic compounds, you can number from clockwise or you can number counterclockwise. Whatever one gives you the lower number branching. Okay, so this is going to be 1 ethyl. 1, 2, 3, 4. Methyl. Cyclopentaane. So,
It's on the 3rd carbon. So it should be 3.
oh, it's on the 3rd one, yeah. Yeah, so this is carbon number 3. So 6 is the magic number. Why it's so stable has to do with the bond angle. Now in 305, you talked about Lewis structures, remember? And then you went in and remember you did the valence shell electron pair repulsion, VESPR? And whenever you had a tetrahedral, the angle was 105, 104.5 degrees. That's the perfect angle. And cyclohexane, that angle is 105.4. That's why it's so stable. Okay. Now I mentioned that carbon-carbon single bonds freely rotate, except cyclic compounds do not freely rotate. Also, double bonds don't freely rotate. But for alkanes, though, what we're talking about is they're rigid. So we can have these two compounds. One is cyclopentane, 5 carbons, each one 2 branches. But they aren't the same molecule. It has to do with the relationship between the branches. The one on the left, the branches are on the same side. The one on the right, the branches are on opposite sides. So, hence cis trans. Now, most of you are aware of fatty acids. Oh, fatty acids that are trans are not natural. So when you have trans fats, deep fat fried foods, sometimes they'll have trans fat in them. That's very unnatural for your body. Now, what part of the cell is made up of fats? Yeah. Hmm? Okay, what's different between one cell and the other? What differentiates between the two? Cell wall or the cell membrane, same thing. Those are made up of, they'll say phospholipids, which are fatty acids. The fatty acids are assumed to be cis. Cis fatty acids look like this. They have a hooked tail. Trans look like this. So your membrane is not going to function very well with trans fats because it's looking for the cis ones, which are hooked. I used to give a essay question. So I went to my doctor. I was starting to have problems. Ever since I started eating a lot of deep fat fried foods. And he said, you probably have your cell walls and membranes messed up because of the trans fats. That would be the answer, the diagnosis. How to fix it? Stop eating deep fat fried foods. Easier said than done. Okay, so the cis, think of sister, close together. Trans, think of transcontinental. That's why I remember. So, what's different about these two?
I have a question, I'm sorry. Where does the di from the dimethyl cyclopentane come from?
What dots?
DI, the beginning, the prefix?
CIS?
No, the DI, where does that come from?
Dies two.
But it was like two branches?
2 methyl branches, yeah.
Oh,
Okay, So what differentiates the names on these is the cis and trans. Because they're both going to have branches at carbon numbers 1 and 2. It's just that the relationship between the branches are not the same. So the name has to be different. Okay, so cis, think of sister. Transcontinental. Remember the airline? Transcontinental. Okay. Physical properties. Now I'm going to be getting into intermolecular forces in depth in this class. Because that's what makes things boil higher, have higher tension, melt higher, is how strong the intermolecular forces are. Now, sometimes molecules have polar and non-polar parts to them. They're called surfactants or soap. Now, we're going to be making soap in this class. That's your second wet lab. First one, actually, excuse me, it's your third wet lab. Second one is we're going to be distilling orange essential oil out of an orange peel. Then we're going to use that to flavor our soap for fragrance. Okay. So if you look at the size of alkanes, starting from 1 carbon long to 10 carbons long in this case, notice what happens. The boiling point goes up. Melting point goes up. And the surface tension goes up. And this is true for any series of molecules. Now, in this chapter is on alkanes, so we're talking about alkanes here, but this is going to be true for alcohols, ethers, aldehydes, ketones, fatty acids, esters, amines, amides. They're all the same. The longer they get, higher boiling point, higher melting point. And this is a series of, we're going to have a series of graphs like this, okay? Only we're going to have different groups represented on the same graph. But since we only studied alkanes so far, there's only one line item. And this is the graphic version of that. Okay, bonding characteristics. I used to cover this in depth, but remember 1s, 2s, 2p, all that stuff from 305? Oh, darn. Okay. Reactions. Now, there are 3 parts to every test: naming, intermolecular forces, and reactions. After a while, naming is like second nature because you do enough practice. Intermolecular forces, same thing. Reactions are another story. So, reactions are what happens when we start with a reactant product. Now, because energy is being given off, that means the products are more stable than the reactants. If energy is required for the products to form, that means the reactants are more stable than the products. Now, when you have a cold pack, there's a little glass ampoule in there, you break, and everything gets cold. That's called an endothermic reaction. In that situation, the products are less stable than the reactants you're starting with. That's why it gets cold, because it's pulling energy from your hands. A hot pack is the opposite. We have a fire, we have combustion. We produce heat. That means the fuel we start with is less stable than the products, carbon dioxide and water. Now, I'm going to hold off on reactions till Wednesday. Alkene reactions are more complex than alkane reactions. There are only two reactions for alkanes. One is called combustion. And the other one is called halogenation. And remember, the halogens on the far right, next to the noble gases. Fluorine is at the top, and it goes chlorine, bromine, iodine, etc. When we put those on an alkane, that's called halogenation. So we're starting with a alkane with a halogen. I end up with the halogen bonding to the alkane. Combustion reactions require a spark. They just don't happen. So we can have gasoline sitting here on the table. Nothing happens. It only happens when we add a spark. And then boom. Okay, so combustion requires spark. Okay, I'm going to do one more thing, and that's going to be it for today. Okay, I put together this a long time ago. And these are the reactions you're going to have in Unit 1. And all we've talked about so far is halogenation and combustion. I'm going to talk to you about how to read this on Wednesday. Now, usually your hand goes up. Do we have to memorize that? No. I'm going to give you this for your first test. Okay. I have a Unit 2 reaction sheet, just like this. I add to it. In Unit 3, I add it again. So this thing keeps getting more and more complex. I want you to be able to look at what you're trying to make and then how to put it together to make. That's what we're going to do with reactions. Okay? Now, at the beginning of the Unit 1 dry labs, that's there, this chart. Okay. So that's what I wanted to cover today, alkanes. Now, on Wednesday, I'll have less startup time, but we're going to cover much more detail, reactions of alkenes. Along with that are going to be reactions of alkanes. Okay. All right. How are you guys doing? Isn't this different than 105, 305?
Hey,
Yeah, really different. And our lab are going to be in 315, not 316 like last semester.
okay.